Professor Fiore here. How you doing, folks? I would like to discuss the issue of startup transients in simulations. Let's take a look at a very simple circuit. We have a voltage source, a resistor, and a capacitor. If you're not aware of the issue of a startup transient, this can royally mess up your interpretation of the output from your simulator when you're doing a transient analysis, in other words, a time-based analysis. As a matter of fact, you may have noticed many times that when I do a transient analysis, I pretty much habitually skip over the very beginning of the simulation. In other words, I'll start not at time t equals 0, but maybe 1 millisecond in or 10 milliseconds in, something like that. There's a good reason for that. So in this case, right, I have a 5 kilohertz sine wave coming in. We can calculate the value of the capacitive reactance, which works out to minus J 318 ohms. And if you do a little voltage divider between the 1K and this 100 nanofarad capacitor, again at 5 kilohertz, you'll discover that you'll get maybe about 30% or so of the input signal. So in our case, we're expecting maybe 270 millivolts peak, given a 900 millivolt peak input. Okay? And we would expect, of course, there to be an appropriate phase shift, right? This is a capacitive circuit. We know that voltage across the capacitor cannot change instantaneously. So we expect to see some lag. In other words, the capacitor voltage occurring later in time compared to the input voltage. And of course, sort of the flip of that as far as the resistor, because the resistor voltage and the capacitor voltage are going to have to add up to whatever the source is, given Kirchhoff's voltage law. All right, what I want to do right now is just look at a transient analysis. So we are going to start here at time t equals 0 and go to 1 millisecond. Now at 5 kilohertz, that's going to give us 5 cycles of the input. All right. Okay, let's drag this down here so we can see it a little better. And let's get a legend on here. And because we have sort of two different greens here, what I'm going to do is I'm going to take this one and I'm going to change the color on it just so it's a little bit more obvious for us. Let's change this to, what do you want to do? Let's see, what do we got? How about blue? Yeah, that's a little better. Okay, so the sort of olive green out here, this is the generator, the input signal, right? That's our 900 millivolts. The blue is the voltage across the resistor, and then the red, this sort of maroonish, that's the capacitor voltage. So what we notice, you know, if you take a quick look, you might not notice, but if you just take a moment, you notice the front end of this, right, in the first few hundred microseconds, is not quite the same as what we have out here, you know, after, say, 500, 600 microseconds. In fact, a close look also shows that a similar kind of weirdness is happening with the voltage across the resistor. You know, it's peaking over here low, and then it's getting a little bit higher. The capacitor is sort of the exact opposite. It peaks a little too high, and then it starts to work its way back down. So once we get out here, you know, in this like 500 microsecond plus region, everything seems to be stable. Everything seems to have settled down. So what I'm really sort of focusing on here is this business. What is going on over here? This is what we call the startup transient. Now, the thing to remember in this, at least in this circuit, voltage across the cap cannot change instantaneously, and none of these components have any kind of current or voltage, you know, through or across them at startup. So we would say VC is 0, right? The voltage across the resistor would be 0. The source is 0. As soon as the source starts to increase in amplitude, right, we start to see the voltage across the resistor and the capacitor also increasing, right? So this thing is starting from 0. And notice that initially, at least at this very, very front end, the resistor and input voltages are perfectly in phase, all right? And then we see as time goes on, we start to see the phase shift that we expect to see. And if we come out over here, we can see, all right, the voltage across the resistor is leading a little bit, and clearly the voltage across the capacitor is lagging, right? Lagging by quite a bit, okay? So, what the heck, what's the deal, all right? Why is it happening? That's sort of an important question. But secondly, how do we avoid it? Ultimately, what really is important is that you understand that this can occur. If you just did a simulation on this from 0 to 400 microseconds or something like that, you just want to see the first couple of cycles, well, you could easily get the wrong idea of what the output waveform looks like, right? You have this thing, and you're going to think maybe it's some kind of weird asymmetrical sine wave, or maybe it's a sine wave with a DC offset, something not quite right. But when we get into the steady state thing, we can see, yeah, there's several cycles here. They're pretty much identical. And if you extended this out, if you ran this out to 10 milliseconds or whatever, you would see it is in fact consistent, right? Once we get out here, it's consistent. Okay, so, as I said initially, voltage across cap can't change instantaneously, so it has to start at 0 and work its way up. But we do know there is this differential relationship as far as the voltage and current on the capacitor. And when we get a little further along, right, we notice that when the sine wave on the input is starting, okay, in other words, at 0, out here we can see that this sine wave across the capacitor is in fact negative. It didn't start at negative, right? It started at 0. But out here, at that same instant in the cycle, it is in fact negative. Well, how negative is it? Because this is going to be important. All right, so I'm going to just move this along until we're just about crossing 0. All right, so right here, I'm talking about crossing 0 at the input signal, at the input sine wave. What do we have? We're looking at about a -1/4 of a volt, right? This says negative 252 millivolts, but we can say about a -1/4 of a volt, right? Well, it doesn't start at a -1/4 of a volt. It starts at 0. So it's almost like the sine wave has a positive bias, a positive offset. And you might be thinking, what do you mean positive? Isn't this thing off by a -1/4? Yeah, it should be down here at a -1/4 of a volt, but it's actually starting at 0. So it's as if you had the sine wave starting off a 1/4 of a volt positive, 1/4 of a volt more positive than it should be. All right? And the end result is this thing sort of has to discharge, if you will, that extra 1/4 of a volt. Now we can prove this rather nicely by coming into the cap and putting in an initial voltage, right? So I'm just going to come in here and set this to that -1/4 of a volt that we're supposed to have, okay? I'm going to redo the simulation, but one slight change. I'm going to select use initial conditions. So this is in fact going to use initial conditions that we set, like a capacitor voltage or maybe an inductor current, something like that. We're going to rerun it. Boom, look at this. All right, so that red is still the capacitor voltage. And notice this is nice and stable because it's basically starting off where it's supposed to start. In other words, well, maybe supposed to isn't the right word, but it starts off where it would have been in the steady state case once everything had settled down, once we got past the startup transient, okay? And we can see that the voltage across the resistor, which is this green one I had turned into blue last time. So let me just, to be consistent here, so we can switch around between these and still talk about the same colors. So that actually looks like, it's nice and stable now, right? Unlike the very first one we did, right, where we started off kind of low and then worked its way up. Now that we've given the appropriate offset to the capacitor, everything seems to be, copacetic. Everything seems to be proper. All right. Okay, so the next question is, well, how do I determine how long this transient startup issue occurs? do I have to wait for a millisecond? Do I have to wait for 10 milliseconds? Well, it turns out that it varies on the signal frequency that you're using and the component values. And that probably shouldn't be too surprising. For many of the circuits that we work with, here on the AC circuits course and in your basic, audio amplifiers and things like that in the semiconductor videos, waiting a few milliseconds, maybe 1 millisecond, maybe 5, maybe 10 sometimes, will normally be sufficient. And you'll find that when I do videos, that's usually what I do. I'll delay the start at maybe a millisecond or 10 milliseconds. So how do we determine that? Well, there is a little trick, right? In a simple circuit like this, it turns out to be fairly quick. It all falls back to the RC time constant. So I'm going to switch over to a slight variation on this circuit. I'm going to replace the sine wave with a step function. So this is just 0 volts, and then it's going to jump up to 1 volt and stay there. It's not going to flip back and forth. So this is kind of like, when we first looked at RC circuits, we have a DC power source and a switch. So that's really what we're doing here is we're simulating that switch. We're just going to energize the circuit at 1 volt at a certain time and see what happens. So what do we expect to happen? Well, if I'm looking at the voltage across the cap, right, it's going to start at 0 and it's going to charge up to whatever the source is. It's going to charge up to 1 volt. Meanwhile, the resistor is going to start at the 1 volt and work its way down to 0 volts. So if we do a transient analysis on this, right, this shouldn't be too surprising. Right, there we go. And let's get our thing out there. Okay, so here's VC. Like I said, starts at 0, works its way up to the 1 volt. Up here is the 1 volt that we put in for the generator. And the resistor voltage, right, starts high, works its way down. Okay, now let me just move this out of the way here for a bit. Shrink this down a little. And that circuit, right, your time constant, RC, is the 1K times the 100 nanofarads. Okay? 1K, 100 nanofarads. That's 100 microseconds. And we know this thing should be stable after, reach steady state, however you want to say that, after 5 tau, after 5 times the 100 microseconds. In other words, after 500 microseconds, we should be pretty much there. We'll be within, 98, 99%, right? So when we look at this, in fact, when we get to 500 microseconds, here's 5 tau, right? We can see that the resistor voltage has gone pretty much to 0, and that capacitor voltage is pretty much maxed out, right? Not perfect, but pretty stinking close, all right? Now let's go back and look at the very first plot that we did. So here's the capacitor, right? It's starting high and going low. Here's the resistor, it's starting low and going high. How long does it take to get to the more or less steady point? Well, it's about 500 microseconds, right? Yeah, I know at 500 microseconds, it's pretty good. When you're down here at 250, it's mostly the way there. Not fully, but it's pretty, it's pretty well on its way. The majority of the change has occurred, over 80% of the change has occurred. And when we come back here and look at 250, we can say, yeah, this peak is not quite as high as these peaks. All right, this one right here is maybe not quite as negative as these peaks, but we're pretty well there, right? We're getting there. We're almost there. And by the time we get to 500, we are there, right? For all practical intents and purposes, within 1 or 2 percentage points, we're there. Okay, now the sharp-eyed viewers might notice, hey, VC over here is falling. It's starting high and going low, and VR is starting low and going high. But when we did this, VR is high and goes low, and VC is low and goes high. What the heck is the deal? Those two things seem to be backwards. Well, this goes back to the bias I was talking about, right? That little offset bias. The reality is the capacitor is starting, in our case, a 1/4 volt too high. So instead of thinking in terms of a charge cycle, we actually have to think in terms of a discharge cycle. So this cap is actually charged up to a 1/4 volt, and we turn the system on and it has to discharge. And you might remember, right? When we looked at RC circuits like this, the discharge curves are the swap of the charge curves. In other words, if this was a pulse that was high back here and then was going low, the green would represent what the capacitor is doing instead of the resistor, and of course the red in this case would just go out to zero, but it's the capacitor I really care about. All right, so that capacitor would be discharging, and that's essentially what we're seeing back here. All right, this is following the discharge curve. This cap, the maroon, is following the discharge curve. Right, because like I said, it's really starting a 1/4 of a volt too high, as we proved over here. Right, when we biased it down a 1/4 of a volt, everything was nice and stable. All right, okay, so bottom line, when we wrap this whole thing up, when you're doing simulations, you must be aware of the fact on a transient simulation that the very beginning of the sim might not be perfectly accurate compared to the steady state. Right? You get these weird things. Like I said over here, it looks like the resistor is actually in phase. It's really not. Okay, you know, the amplitude and the phase on the capacitor, that's also not correct. You have to wait for that transient to settle out. Okay, how long does that take? You know, in some circuits, you know, if we were going to use considerably, let's say, lower frequency, you might not even notice the startup transient. You know, compared to the cycle time, you know, if the cycle time is really long, you know, if we were using like 100 hertz or something, yeah, I mean, after a 1/4 of a cycle, this thing will have settled out, right? So it all depends on the sizes of the components and the frequency that you're using. You can figure out in a circuit like this, you can figure out very quickly, you know, a 5 tau value and just go beyond that. Okay, you know, depending on what your input frequency is, just go out to that point, start there instead of starting at 0. Now, I need to emphasize this is not NOT, this is not a quirk of the simulator. This is not some mathematical sort of screw up on the part of the simulator. This is really what happens. If you were to build this circuit in lab, guess what? The cap starts off with no volts, right? It's not charged. So this is really what does happen. You never notice it in lab, though. You know, you don't notice it because by the time you turn the power on, you are many, many milliseconds out here to the right. You never see this thing settle down. You'd have to put in some pretty extreme values to actually watch this thing occur on your oscilloscope. So, you know, by the time you turn the power on and, you know, apply your scope probe, bump, transient's long, long gone. All right. But in the simulator, you know, it's kind of like you're slowing down time, right? You're taking a snapshot here. You can start at the very instant that the circuit's energized, and you see this weird little transient, right? So it's not a quirk of the simulator. It's real. There are ways around it, right? So, you know, you can do this little trick like I did down here. And, you know, this is, I really would use the word trick, okay, to try to get around that. Because it kind of presupposes knowledge of what's supposed to happen, right? But it is a real thing. And, you know, you can do some computations with a simple circuit like this on how long it should take for it to settle out. As a rule of thumb, like I said, for the kinds of circuits that we're using with these sorts of values, same thing with like an audio amplifier. If you wait just a few milliseconds, you know, without having to grind through the computations, that's probably going to be sufficient. But even if you're not sure, right, just look at it. You know, when you do something like this, just look at the front end and look for an asymmetry in the peaks, right? Is this positive peak a lot bigger, you know, than the magnitude of the negative peak, or vice versa? Because, you know, you could have something that's going the other way, all depending. And of course, that will also partly depend on this source signal that you're using. Are you using a sine wave, using a cosine wave? These things are going to have different effects. You know, is this an inductor instead of a capacitor? You know, how complicated is the circuit? But you want to look for that trend, right? Is the waveform like consistent all the way through the time plot region? You know, from where you start to where you end, or you're seeing some kind of trend where it's building up or it's falling down, or, you know, something like that. Okay, so just keep that in mind when you do these kinds of simulations, right? Whenever you do a transient simulation, keep that in the back of your mind. It's important. It's not lying to you. The simulator is not broken. It's just that from a practical standpoint, you typically would not see this occurring in lab, right? Okay, questions? Put them down in the comments. Take care, and we'll see you next time.